Hi everyone, welcome back to our seminar. Today Yuval Wigderson is going to talk about the limits of the inertia bound.
Okay, yeah, thank you, Maria, and thanks to all the organizers for inviting me to be here. So, yeah, as I was saying, it seems like a very nice seminar, and I'm very glad to be here. So, yeah, today I'll talk about this recent work with Matthew Kwan, who's a professor at IST Austria, about the inertia bound. So, just to give you an idea, I'll start with some general introduction to both the ratio bound and the inertia bound. Then I'll tell you what the main topic of the talk is. And I hope to be able to give a more or less complete proof sketch of the main result. So let's get started. So I'll just start with some general background on spectral graph theory that I assume everyone here knows. But yes, the adjacency matrix, everyone knows, it's the matrix of zeros and ones where ones represent the edges of a graph. And maybe to this audience, this isn't so amazing, but I really find this amazing that the adjacency matrix, if you think about it, it's really sort of another data structure. It's just a way of encoding the edge relation of a graph. And it's not really a matrix because it's just sort of an array of zeros and ones. But if you insist that it is a matrix and try to do linear algebra to it, that actually is useful and it tells you a lot about the graph. So linear algebraic properties of the graph, sorry, of the matrix are related to graph-theoretic properties of the graph. I just find this astonishing. In this talk, we'll actually be working with a slightly more general object, which is what's called a weighted adjacency matrix. So a weighted adjacency matrix is just like the adjacency matrix, except where before I had a 1, I'm allowed to put any number, positive, negative, 0. I have to keep it symmetric. That's a condition I'll impose. And the only other condition is that when there's a non-edge of the graph, I have to put 0. So I start with the adjacency matrix, and I can turn all the ones into whatever I want while maintaining symmetry. And an extension of the amazing fact above is that many of the amazing connections actually go through even in this more general setting if you generalize them appropriately. And this is extremely useful in graph theory. You can often learn a lot about graphs from this. And often a main difficulty or a big difficulty is sort of understanding what is a good weighting to choose. So what is a good weighted adjacency matrix to choose? And so a nice recent example of this, a few years ago, Hao Huang proved this thing called the sensitivity conjecture, which was a major open problem in computer science for like 30 years. And basically the proof is like a page or 2 pages. And it boils down to using a well-known connection between graphs and adjacency matrices, specifically between the maximum eigenvalue and the maximum degree, noticing that it works for weighted adjacency matrices, and then like picking a good weighted adjacency matrix. And in some sense, the hardest part of his proof is finding this good weighting. And a sort of general problem that I'm very interested in is, given a graph, what can you say about the space of all weighted adjacency matrices of this graph? And for some property of interest or some quantity of interest, how can you optimize this over the space? And so that's sort of the overarching question that's driving this talk, and many other things that I do and other people do. So one very important connection between graphs and linear algebra is the so-called ratio bound. And it says the following thing. So it's due to Hoffman. And it says the following thing. If I give you a graph, which is regular, its independence number is upper bounded as some function, this function, of the smallest and largest eigenvalues of its adjacency matrix. And I guess the number of vertices. And this is a very, very useful result, as I'm sure everyone here knows. So for example, you can use it to give a very short proof of the Erdős-Colorado theorem from extremal set theory. And along the lines of what I was saying before, there's a weighted version of this, which I think was first observed by Lovas. And it says the following thing. It's the exact same inequality, except now I have an arbitrary weighted adjacency matrix of the graph. Before I had the assumption that the graph is regular, now I'll assume that all the rows of this matrix have the same sum. And then this same inequality holds. And the thing I want to say is that this weighted inequality is sort of even more useful. So I think the first person to really notice this was Wilson, who used this weighted version to prove big generalization of the Erdős-Colorado theorem. And going with the ideas I was saying before, some of the difficulty when you want to apply this theorem is how to pick a good weighting. So basically, Wilson, in proving this theorem, he found a good weighting of a certain graph, and that he applied this result and was able to get a theorem. Okay, so any questions about that? And of course, sorry, I should have said this earlier, but you should feel free to interrupt at any time if you have any questions.
Yeah, so the Lovaas bound also works if the condition on zeros is that you can change zeros to anything which is, I think, non-positive.
Yeah, I think that's true, except that, I think that's true.
So, but
yeah,
you're
for
not
now, I'll stay. Yeah, so Lovaas somehow proved an even stronger thing than Hoffman's bound. Yeah. Does that answer the question, Yuval, or is there something?
Yeah, I just wanted to ask whether you're going to, whether the inertia bound also works for this.
No, so it won't. Yeah, so soon I'll say the inertia bound, and it won't work under a sort of more general notion of a weighted adjacency matrix, I think.
Okay.
Yeah. Any other questions? Okay, so again, as I was saying, we have this weighted ratio bound. And given this, you can view it as an optimization problem. Like if you have a graph and you want to get the strongest possible bound on its independence number, then you have this optimization problem on the space of all weighted adjacency matrices to minimize this quantity, which is sort of the type of general question I was talking about earlier. And it turns out that this is actually a fairly well-behaved optimization problem. So in particular, if your graph happens to be highly symmetric, this is fairly straightforward. So for example, a nice result that Lovaas proved is that if your graph is edge transitive, then actually this minimum is attained on the unweighted adjacency matrix. So if your graph happens to be edge transitive, then you don't even need to consider the weights at all. The unweighted bound is the best you could do. And even if you don't have such a strong symmetry condition, but you know something about the symmetries of the graph, you can apply representation theoretic techniques. You work in this object called the Bose-Messner algebra. And by using representation theoretic techniques, you can basically figure out what the best weighted adjacency matrix is. And this was the technique that Wilson sort of introduced into this field when he proved this, this generalization of the Erdős-Corrado theorem. And even if your graph doesn't have any symmetries, you can check that this problem, optimizing this quantity, is actually a semi-definite optimization problem, if you rephrase it appropriately. And so if I just give you an arbitrary graph, you can actually compute what the best weighted adjacency matrix is in polynomial time. So this optimization problem is in some sense fairly straightforward. We know how to tackle it. So any questions about that? Right. So now I want to introduce the inertia bound, which is sort of in some ways similar and in some ways rather different. So just some notation, I'll denote by this n greater than or equal to m, the number of non-negative eigenvalues of a matrix. And the inertia bound says that for any graph, its independence number is at most this quantity of its adjacency matrix, the number of non-negative eigenvalues of the adjacency matrix. And it's a rather pretty result. It's one that, I learned the ratio bound when I was an undergrad in my undergrad combinatorics class, and I never learned the inertia bound. And it's something I wish I had known. So I bet many people here have seen it, but just to be on the safe side, I'll show you a proof of this. It has a very short proof. So let this n denote the span of all the eigenvectors of the adjacency matrix, which corresponds to negative eigenvalues. And the simple observation is that if I take any non-zero vector in this space and I take this quadratic form, I'll get something negative because it's spanned by the negative eigenvectors. On the other hand, if I pick some maximum independent set in the graph, and I let this z denote the set of vectors whose support is just in that maximum independent set, then the observation is that for every vector in Z, if I look at the same quadratic form, I get 0. Because it's supported in this independent set, the adjacency matrix has all zeros in that block. So when I multiply V by the adjacency matrix by V, I'll just get zeros. So if you compare these two conditions in blue, you see they say different things. And so therefore, these two subspaces have to be disjoint. The ambient dimension is at least the sum of their dimensions. And we know what their dimensions are. So the dimension of Z is just the size of this largest independent set. And the dimension of n is precisely the number of negative eigenvalues, which is n minus the number of non-negative eigenvalues. And so rearranging gives this result. So everyone happy with the proof? Okay, even if you're not, I'll show you another proof, which is even shorter. It's actually the same proof, but it's just sort of a different way of looking at it, which is just this largest independent set. As I said, it's a block of zeros in the adjacency matrix. And then just Cauchy's interlacing formula says that the number of non-negative eigenvalues of the whole matrix is at least the number of non-negative eigenvalues of any principal submatrix. And the submatrix of all zeros has only 0 as an eigenvalue. So you get this inequality. And if you unpack enough, you'll see that these are sort of the same proof. But hopefully you liked at least one of them. And so you believe this is a true theorem. And if you look at this theorem or at these proofs, you'll observe that we never actually used anything about the entries of the matrix besides that we got a block of zeros from an independent set. And so this theorem naturally generalizes to the weighted setting. It says the exact same thing. If I give you any weighted adjacency matrix of the graph, the independence number is at most the number of non-negative eigenvalues of that matrix. And as far as I was able to figure out, this was first observed by Calder-Bank and Frankel in the 90s, but maybe someone knew it earlier. This kind of result was rediscovered many times by many different people. So now that we have such a result, we of course want to ask the natural optimization question. Or actually, sorry, maybe before that, I should say that this simple result with the short proof is again very useful and very powerful. So actually, again, it gives you another very short proof of the Erdős-Corrado theorem. However, as before, many of the applications, you really do want the weighted version. So Erdős-Corrado you can do with the unweighted version, but for many other applications, you would want to use the weighted version. And so we again end up with this new optimization problem, which is just among all weighted adjacency matrices, to minimize this quantity, the number of non-negative eigenvalues. And maybe surprisingly, maybe not surprisingly, this is a much sort of worse behaved optimization problem than we had before. So for example, I told you that the ratio bound is efficiently computable. I don't know that this one is efficiently computable. In fact, I don't even know whether it's an NP, sort of figuring out what the optimal bound you can get from this is. Last time I spoke about this, I said that I don't even know if it's decidable. And at the end of the talk, Noga alone came up to me and showed me how to check that it is decidable. So maybe at the end of this talk, someone will tell me why you can see that it's an NP, but I certainly don't know whether it's an NP. So that's one way in which this is badly behaved. Another way, we saw that for the ratio bound, symmetry is very useful. If the graph is symmetric, we can say a lot about the optimization of the ratio bound. And for the inertia bound, that's just not true. Like you can use symmetry to get heuristics, but often symmetry is actually just really bad. So a nice simple example is if you consider just a complete bipartite graph, its ordinary adjacency matrix has eigenvalues t, minus t, and 0 with high multiplicity. So the number of non-negative eigenvalues is actually just one less than the total number of vertices. So if you just plug this in with the unweighted inertia bound, you'll get the true statement, but the very weak statement that the independence number of ktt is at most 2t minus 1. And so that's not very interesting, but you can observe that if you pick weights in some sort of unstructured way, so for example, if you just assign a random number to each off-diagonal entry in the adjacency matrix, then you will actually get the optimal bound, that the independence number is at most t. So this is sort of in sharp contrast to the ratio bound, where we had this result of Lovász that for edge transitive graphs like this one, for the ratio bound, the unweighted adjacency matrix is best. But here we see that rather the opposite is true. The unweighted adjacency matrix does very badly. And to get a good result, you sort of want to pick weights that have no structure. Okay, so any questions about any of that? Okay, so if not, I'll move on to the next part of the talk, which is about the limits of the inertia bound. So again, this is the inertia bound that we now hopefully all know and love. And as I was saying, it's very difficult to understand what the optimal weighted adjacency matrix is. And therefore, it's very difficult to know how good this bound actually might be in general. And there's a natural question that I think was first asked by Chris Godsil about 20 years ago, which is whether this bound is just always tight. So in other words, is it the case that for every graph, you can always find a weighted adjacency matrix such that you actually get equality here? And I mean, I think when I first heard this question, I thought it's sort of crazy. I mean, there's no way this could be true. And indeed, it's not true. So it took almost 15 years. But Cvetković was able to prove that if you look at the Paley graph of order 17, you can check that its independence number is 3. So that's pretty easy to check. What's rather difficult to check is that for every weighted adjacency matrix W, it has at least 4 non-negative eigenvalues. And thus, you do not get equality for this graph. And I mean, this answers the question, but this proof is quite messy. It has a lot of casework. It's extremely specific to just this Paley graph. It doesn't seem to work for any other Paley graph. And so you might be interested in, are there more robust ways of answering this question? I mean, so now we know the answer is no, but can we get sort of more examples showing that the answer is no? Okay, so yeah, it turns out that we can. So a few years ago, people realized that you can also approach this question about the limits of the inertia bound using quantum graph parameters. So there's a thing called the quantum independence number, which was defined by Mancińska and Robertson. It's a parameter, a graph parameter, which is always an upper bound on the independence number. And I won't say anything about the definition because it's pretty complicated and I actually don't understand it all that well. But it's sort of motivated by viewing the independence number as some sort of game and then imagining what would happen if you set up that game with entanglement. And then doing that allows you to define this quantum independence number. And one thing that Mancińska and Robertson proved is that there's a separation. There exist graphs for which the independence number is n to some power less than 1, whereas this quantum independence number is actually at least n over log n. And thus, there exists sort of infinitely many graphs where the quantum independence number is really quite a bit larger than the normal independence number. And then a few years later, Wojciech, Elfik, and Abiad noticed that the inertia bound actually also works as an upper bound on the quantum independence number. So for any weighted adjacency matrix, its number of non-negative eigenvalues is at least the quantum independence number. Or equivalently, the quantum independence number is sandwiched between the two sides of the inertia bound. And so if you just combine these two results, you'll find an infinite family of examples where you have a separation between the independence number and the inertia bound. Because these examples, the independence number we know is n to the 0.9, and the inertia bound is at least this quantum independence number, and that's n over log n. So this is a sort of more robust infinite family of examples showing that the inertia bound is not always tight. So any questions about that?
So how does this compare to Shannon capacity?
How does the quantum independence number compare to the Shannon capacity?
Yeah.
So I believe it's not known, actually, but maybe some quantum independence experts can correct me.
Okay, I'm not an expert, but I do think they are related. And then originally, the graph that has the first one, I think, that is known to have separation between the independence and quantum independence number, the smallest one at least, was also used to study the zero error quantum channel capacity.
Any other questions? Thanks, Maria. Yeah, so I won't really say much more about the quantum independence number, but I do want to get back to Godsil's original question of whether the inertia bound is always tight. Okay, so we know the answer is no, but again, there's many other questions you could ask. So for example, you could ask a quantitative question of how big can the separation between the independence number and the inertia bound be? And another question you could ask is, okay, maybe the inertia bound isn't always tight. I mean, we know it isn't, but maybe it's still somehow the best sort of bound that you can get purely based on eigenvalues. So in particular, it is a sort of hard question to formalize, but you could ask whether the inertia bound is always at least as strong as the ratio bound, because that would show that it's, at least better than this other spectral bound. And so these are two of the questions that we were thinking about. And basically the answer to both of them, the answer to this one is no, and the answer to this one is pretty big. So the main theorem that I want to tell you about with Matt is that if I give you any C4 free graph, and I give you any weighted adjacency matrix of it, the number of non-negative eigenvalues is at least this number, at least 23% of the number of vertices. And so in particular, you can get a very large separation because if you think of your favorite example of a C4 free graph, then hopefully you're thinking of my favorite example, which is the polarity graph of a projected plane. That's an example of a C4 free graph with the property that the ratio bound shows you that the independence number is of order n to the 3/4. And in fact, so is the quantum independence number. So the ratio bound proves n to the 3/4, whereas our theorem tells you that the inertia bound could never do better than a linear bound, just 23%. So for these graphs, you have a very large separation between the truth of n to the 3/4 and the best possible inertia bound, which is at least 0.23 n, and also a very large separation between the ratio bound and the inertia bound. So the ratio bound in these cases is much better than the inertia bound. So any questions about the statement of the theorem?
So what is the SDP for the ratio bound? Is it related to the theta function?
Yeah, so it sort of depends how exactly you want to set it up, but yes. Yeah, so you can phrase the ratio bound as because the maximum eigenvalue, because the minimum eigenvalue is involved, it's something about what's the smallest multiple of the identity you need to add to get it to BPSD. And if you set it up like that, you actually get essentially the same SDP as for the theta function. Yeah. Any other questions? Okay. So the rest of the talk, I just want to spend proving this theorem. So that's what we're going to do from now on. So again, the theorem we're trying to prove is if I have any C4 free graph and I have any weighted adjacency matrix of it, the number of non-negative eigenvalues is at least 0.232 times n. So, all right, let's fix some weighted adjacency matrix and let's let its eigenvalues be λ1 through λn. It's helpful to think of this probabilistically. So it's not really necessary, but it's, I think, a good way of thinking about it. So let's let x be a random variable that just picks one of these eigenvalues uniformly at random. So in the random matrix theory literature, they call this the empirical spectral distribution. But just, yeah, it has one of these n possible values, and it takes each one with probability 1 over n. And then, of course, we want to prove that the number of non-negative eigenvalues is at least something that's the same as proving a lower bound on the probability that this random variable is non-negative. So we want to prove a lower bound on this non-negativity probability. Okay, so when you have a random variable, probably the first thing to think about is what's its mean. So the mean is very easy to compute. The mean of this random variable is 0 because the sum of the eigenvalues is 0, because it's just the trace of the matrix W. And then, okay, after you know the mean, you might want to know the variance. And for that, you can just observe that this whole problem is invariant if we scale the matrix by any constant. If we multiply all the entries by 10, that doesn't change the proportion of eigenvalues that are non-negative. So we can always rescale the matrix and assume that the second moment of this random variable is 1. Just for simplicity, it doesn't really affect anything. Okay, so then you could hope, I mean, is it enough to know the first moment and the second moment? Is that enough to say something about this probability of non-negativity? And the answer is no. So basically, just knowing the first moment and the second moment cannot tell you anything about this quantity. However, it's almost good enough in that if you actually know anything about any higher moment, then you're in business. And so concretely, we'll just use this lemma, which says, if I have a random variable with first moment 0, second moment 1, and a fourth moment, which is at most 2, this 2 isn't super important, but it's just what we'll use, then the probability that this random variable is non-negative is at least some constant. It's this kind of funny constant of square root of 3 minus 3 halves, which is exactly this 0.232 that you've been seeing. So this lemma is not so easy to prove, but a version of it where you just get some constant here is not very hard, and I won't prove it, but hopefully everyone believes it. And if you don't believe it, you should try to prove it with some constant on the right-hand side. It's actually a pretty nice exercise. Okay, so given this lemma, and given the fact that we said the first moment is 0, second moment is 1, all we need to do is to get an upper bound on the fourth moment. So we want to upper bound the fourth moment. Well, what is the fourth moment? Just by definition, it's 1 over n times the trace of the fourth power of the matrix, because it's the sum, or it's the average of the fourth powers of the eigenvalues. And then we can explicitly write down what this trace is. It's a sum over 4 parameters, 4 variables from 1 to n of this product of things. Okay, and in general, you have no hope of bounding this. And the reason is that, remember, like the adversary gets to pick the weighted adjacency matrix. So the adversary can get to make some of these entries positive, some negative, some huge, some tiny, and then you sort of have no hope of saying anything about this sum. But, remember, we assumed that the graph is C4 free. And I think now it's kind of clear why this assumption is useful, because if the graph is C4 free, this corresponds to counting closed walks of length 4 in the graph. And if the if the graph is C4 free, then basically a ton of these terms are 0. So you can believe me. So all the terms where I, J, K, L are all distinct go away because the graph has no C4s. And you can believe me that what's left is this. It's some not too hard computation, and it's at most this quantity. So what is this quantity? Well, there's a factor of 2 over n, and then we're summing over all rows of the squared L2 norm of that row. Okay, and our hope again is to say that this quantity is small, like at most 2. And unfortunately, we still can't. And the reason we still can't is that, remember, the adversary gets to pick the matrix. And if the adversary makes it so that some of the entries of W are way bigger than others, that they live at sort of completely different scales, then the large entries will completely dominate this sum because we're squaring. And you basically, this thing will not be bounded by any constant. It'll tend to infinity with n in the worst case. So yeah, so we're still not, we're still not done. This is not nearly good enough. But we get something out of it. So we get that if, for whatever reason, the adversary decides to be nice to us and ensure that every row of the weighted adjacency matrix has L2 norm equal to 1, then we're in business. Then this fourth moment is in most 2. We can plug that into the lemma and be done. So in this extra case, we are done. So any questions about what's happened so far? Okay. Yeah, I mean, this is of course nice if we can get if the adversary happens to be nice to us, but this is a very special assumption. Like, there's no reason to expect that anything that this will be useful for anything. At first we actually tried a bunch of very complicated things to try to say somehow that this case was sort of enough. But the amazing thing, and I find this really amazing, is that there's a really simple reduction that goes from the general case to this case where all the rows of the matrix have L2 norm equal to 1. And so that's the next thing I'll tell you about, is how to reduce to this very special seeming case. So before we go there, I want to digress to a little bit of undergrad linear algebra. So here's a fact that hopefully everyone knows. If I have any matrix and I conjugate it by some invertible matrix, that doesn't change the eigenvalues. So this is a fact that we learn when we first learn about eigenvalues. However, if you do this other operation, which is usually called congruence, so if I multiply on the left by z and on the right by z transpose, this will change the eigenvalues. And you can just write down some small examples, and you can convince yourselves that basically W and ZW, Z transpose, their eigenvalues sort of have nothing to do with each other. Kind of astonishingly, that's only sort of true. So there's this amazing theorem called Sylvester's law of inertia, which says that W and ZW, Z transpose, where Z is any invertible matrix, they'll have totally different eigenvalues, but they'll have the same number of positive eigenvalues and the same number of negative eigenvalues and the same number of zero eigenvalues. And in particular, the quantity we care about, the number of non-negative eigenvalues, is invariant under this congruence operation. Yeah, Sylvester's law of inertia is something I learned when I took linear algebra as an undergrad, and I feel like I didn't really appreciate it at the time. It's pretty astonishing that this operation sort of messes with all the eigenvalues, but preserves the number of positive ones. Yeah, and so that's what we'll use. And another important observation is that if this matrix Z happens to be diagonal, oh, sorry, I should say Z because we're in Canada. If this matrix Z happens to be diagonal, then ZW, Z transpose is another weighted adjacency matrix of the graph, right? Because ZW, Z transpose is just scaling all the rows by something, scaling all the columns by something. We said this matrix is invertible, so none of the things we're scaling by is 0. And so we just get another weighted adjacency matrix of the graph because we don't change the positions of any of the zeros. And remember, we said we were done if we happen to have the magic assumption that every row of the matrix is normalized in L2. So the question that arises from all of this is it possible to pick a matrix Z, which is a diagonal matrix, an invertible one, such that every row of ZW, Z transpose is normalized in L2? And if we can do this, then we're done. So any questions about that? Okay. So this is the million-dollar question. And we're not the first people to ask it. So actually, this is a kind of question that people ask a lot in a field of math called matrix scaling. And matrix scaling is basically questions of the form, yeah, like operations like this, or maybe where you multiply by a different diagonal matrix on the left and the right. Can you ensure some property of the matrix you get at the end with respect to its rows or its columns. Kind of amazingly, there's a pretty deep meta theorem underlying all of matrix scaling. So many results in matrix scaling are of the following flavor. For such a question, whether or not there exists such a matrix Z only depends on the zero pattern of W. So it actually doesn't depend on the entries of W at all. It only depends on where the zeros are. And in fact, there are many theorems of this type that sort of give you an if and only if characterization for when things like this are possible. For our case, we can just pull off the shelf a result that was proved by Chima and Datta in the 70s, although in retrospect, you can also recover it from an earlier result of Sinkhorn. And there's actually an if and only if version of this, but I'll just state a sufficient condition, which is a little simpler to state. So the statement is the following. Suppose I give you a symmetric matrix, and I tell you that it has what I'm going to call no large zero blocks. So that means that if you take any set of rows and any set of columns, such that the submatrix indexed by them is all zeros, then the number of rows plus the number of columns is strictly less than n. Or equivalently, as I've written it here, if you take any set of rows and any set of columns whose number of rows plus columns is at least n, the submatrix on those rows and columns is not the zero matrix. So no large zero blocks, any block of zeros can't be too large. So if I give you such a matrix, then you can find such a matrix Z. So there exists a diagonal matrix Z, which is invertible, and every row of ZW Z transpose is normalized in L2. And I won't prove this theorem. It's actually not super hard to prove, but I won't do it. And the upshot of it for our purposes is that if we happen to know that our matrix W has no large zero blocks, we're done. So any questions about that? Okay. So we're almost at the end of the proof. So again, we're done if our weighted adjacency matrix has no large zero blocks. So let's consider what happens if it does. So suppose there do exist these sets S and T, whose sum of their sizes is at least n, and the submatrix indexed by them is all zero. And basically, geometrically, there's a few different ways this can look. So for example, in case S and T are disjoint, this could mean I have a big block of zeros here where the number of rows plus the number of columns is at least n. And because the matrix is symmetric, we actually get for free another big block of zeros on the other side of the diagonal. At the other extreme, you might have that S equals T. So in that case, you'll just have a submatrix of size at least n over 2, a principal submatrix, which is all zeros. And the general case is basically somewhere between these two cases. So where S and T intersect in some way, and then it looks something like this. And if you look at these pictures, you can start to get a sense of what's going to happen. So for example, if our weighted adjacency matrix W looks like this, then we're just done. And the reason is, if this is W, then it's a direct sum of two smaller matrices, one there and one there. Each of those is, and then the eigenvalues are just the eigenvalues of this guy, as well as the eigenvalues of this one. And each of these is the weighted adjacency matrix of some smaller C4 free graph. So by induction, we can assume that 23% of these eigenvalues are non-negative, 23% of these eigenvalues are non-negative. So in total, 23% of the eigenvalues of the whole matrix are non-negative. So if it looks like this, we're just done automatically. So everyone okay with that? Okay. What if it looks like this? Well, in that case, we're done for actually a completely different reason. So you see, in this case, we're actually just basically in the setup of the inertia bound. Remember, proof 2 of the inertia bound that I gave you told you that if you have any principal submatrix, which is just all zeros, the number of non-negative eigenvalues of the whole thing is at least just the size of that submatrix, just because of Cauchy's interlacing formula. So in this case, we have a submatrix, a principal submatrix of size n over 2, which is all zeros. So in that case, the eigenvalues of the whole thing, actually at least half of them, have to be non-negative. And in particular, at least 23% of them are non-negative. So in this case, we're just done by Cauchy's interlacing formula. So any questions about that? Okay. And in the general case, we're actually just done by a combination of these two things. So it's like a tiny bit of arithmetic plus inclusion-exclusion. But basically, in this case, you're going to get a small matrix there, a small matrix there. You apply induction to each of them. You have a matrix of zeros there. And then maybe you have some extra rows and columns outside of these that you just sort of throw away. But you apply Cauchy interlacing to throw those away. And then you apply this direct sum argument on what remains. And you check just by inclusion-exclusion that you maintain the induction. You get at least 23% non-negative eigenvalues. So in each of the three cases, we're just done by induction plus Cauchy's interlacing formula. So any questions about that? Okay, so that's the end of the proof. So let me summarize it again, just so we all have in our heads the whole picture. So again, the theorem we're proving is that if you have any C4 free graph and any weighted adjacency matrix of it, the number of non-negative eigenvalues is at least 0.232 times n. And again, as we said, this implies that the inertia bound is rather far from tight for example, polarity graphs of projective planes. And it also shows that for such graphs, the ratio bound is much stronger than the inertia bound. And the proof is as follows. So someone gives us this W. If it has large zero blocks, then we just apply this induction plus Cauchy interlacing argument that I said on the last slide. So we reduce to a smaller problem. So we can assume it doesn't have large blocks. And then we can use this amazing matrix scaling fact, this theorem of Shima and Data. And we can find a diagonal invertible matrix Z such that every row of this rescaled matrix, Z, W, Z transpose, which I'll call W prime, every row of W prime has L2 norm equal to 1. So because we've only rescaled rows and columns, W prime is another weighted adjacency matrix of the same graph G. And moreover, by Sylvester's law of inertia, they have the same number of non-negative eigenvalues. So now we let X be the random variable, this empirical spectral distribution for this matrix W prime. And as we said, the first moment is 0, the second moment is 1. And the point of this L2 normalization is that we get that the fourth moment is at most 2. And this is where we use the C4 free assumption. And now we just plug this into this simple probabilistic lemma to say that the number of non-negative eigenvalues of W, that's the same as the number of non-negative eigenvalues of W prime. That's just n times the probability that this random variable is non-negative. And that's at least 0.232 times n. And that completes the proof. So any questions about that? Okay. So in the last couple of minutes, I'll just mention a few open problems that I find interesting. Because there's certainly still a lot to do. It's not like there's still a lot we don't understand about the inertia bound. So one kind of annoying issue is that our technique really seems unable to do anything for graphs that are not C4 free or that have maybe many C4s. So a particularly nice class of graphs that I care about a lot are uniformly random graphs. So you can ask, what does the inertia bound say about GN1/2, just the uniformly random Erdős-Rényi graph? And our conjecture is the following, that with probability tending to 1, as n tends to infinity, you have the property that every weighted adjacency matrix of this graph has at least n over log n non-negative eigenvalues. And the point of this is that it's well known that the independence number of a random graph is only log n, or 2 log n, with very high probability. So if you could prove this conjecture, or even something much weaker, that would show you that for almost every graph, the inertia bound is extremely far from tight. The truth is like log n, and the inertia bound can only prove something huge, like n over log n. I should mention that if you look at our paper, we don't state this conjecture. We state a stronger conjecture, that actually this should really be linear in n. But that's not true. So this was something else that was pointed out to us by Noga alone. So there's a simple exercise that I encourage anyone to try. For any graph, you can find a weighting W such that the number of non-negative eigenvalues is the chromatic number of the complement of G, so the clique cover number of G. Well, if G is a random graph, its complement has the same distribution, and it's well known that the chromatic number of a random graph is n over log n. So there always does exist some weighted adjacency matrix for which this is the answer. So if this conjecture is true, it's best possible. But it would still show a huge separation for almost every graph. So that's one open problem. And as I said, our technique seems totally hopeless here, basically because these random graphs have a lot of C4s. So another conjecture that's sort of in a different direction. So I had talked a fair amount at the beginning about the gap between the independence number and the ratio bound as a function of the number of vertices. But you could ask whether there's sort of just some abstract separation, like a qualitative separation. Namely that, so we make this conjecture, for any k, you can find a graph whose independence number is true, but the inertia bound can't prove that the independence number is at most k. So in other words, there should be an infinite sequence of graphs, I think, where sort of the best inertia bound is arbitrarily far from the truth, which is just independence number 2. And I have no idea how to prove something like this, but I think it's probably true. And my final question, which I mentioned earlier, I think it's a nice question of just understanding what is the complexity of actually computing the best possible inertia bound. So yeah, I mentioned that Noga alone told me how to show that it's decidable. In fact, his proof shows that it's in what's called the existential theory of the reals, which means that it's even in p-space. But is it an NP? Is it NP complete? I mean, I guess probably, but I have no idea how you'd prove something like that. So I think that's another nice question. And yeah, that's everything I wanted to say. So thank you for listening.
Okay, thank you so much, Yuval. Are there any questions for you? Well, I mean, any more questions? If you, do you, can you apply to the triangle-free graphs?
Yeah, so in fact, so if you assume both triangle-free and C4-free, then you can improve our result a tiny bit from 0.23 to actually just a quarter. But if you just assume triangle-free, I don't know how to say anything. And basically the problem is, don't know if I can get to it, but like somehow naturally you sort of encounter something like this. If you try to apply the third moment, there is a version of this lemma with the third moment, but you have to compute the, you have to put absolute values in here. So absolute value of x cubed. And then when you expand that out, you don't get a sum like this that has stuff about triangles. The other thing, I would expect that if you assume stronger girth conditions, like girth at least 100, you should be able to improve this 0.23 to something better. But we actually don't know how to do that. We thought about it a fair amount, and you seem to run into issues, but I think that would be a very nice thing. Yeah.
Okay, thank you. Any more questions?
Can I ask a question? I wonder how tight is your bound, 0.23?
Yeah, it's probably not tight. I mean, I have no reason to assume it's tight. It comes from, where was it? It comes from this lemma. So this is where the 0.232 comes from. for this lemma, that's the optimal constant. But of course, there's no reason to assume that this proof technique or this lemma is sort of the right way of doing it. So the best bound that I know, if your graph is just a disjoint union of triangles, then the true independence number is n over 3. And that's C4 free. So you can't improve 0.232 to any number bigger than a third. But between 0.232 and a third, I have no idea. And I have no reason to assume ours is tight.
Okay, thank you.
My turn? Couple more historical marks than anything. First, thanks for a very nice talk. Second, I never actually thought the answer to my question would be yes, that you would be able to get the
Sorry, I didn't want to suggest
no, you didn't say anything wrong. I just want to make it. I just thought it was a good question. And then John Cvetković found the example with the Prady graph. He and an undergraduate student also found a bunch of other examples, which I don't think ever got written up. But then the paper by Wigderson and Abiad that came out, and so that proved that there were infinitely many cases where the two things were different.
I see. Okay, I didn't know about that. Okay.
Well, I mean, that's not him. Yeah, it's just a historical story. The other point is, I get the impression that you're not aware of the work that Delsart did on the linear programming bound.
Sorry, I am aware of it. I was just trying to keep things uncluttered, but
okay, fair enough. Okay, then I was, because a lot of the stuff or some of the stuff that Lobos did was already in Delsart's work, for example.
Yeah, that's right. So,
but if you know about it, then I have nothing more to say. But
okay,
it was a nice talk. I enjoyed it.
Thanks.
Thank you.
Yeah, so for the Hoffman bound and probably also for this bound, it's surprising that it works at all. And kind of sometimes it works and sometimes it doesn't, and we don't really understand why it works when it does work. So do you have anything insightful to say about it?
No, not really. I have, in fact, the inverse of something insightful to say about this. So yeah, when I thought where to look for counterexamples to examples where we have separation, random graphs was what I first thought of. The reason being that you expect these algebraic things to work very well for structured things and to work badly for unstructured things. Okay, I still believe that random graphs should give an example, but I don't know how to prove it. But the graphs that we show a huge separation for include, for example, these polarity graphs of C4 free, of projective planes. And those are extremely structured. I mean, they're strongly regular graphs. They have huge automorphism groups. And so that actually was very surprising to me. I didn't expect such structured graphs to have such a huge separation. And yeah, so basically the answer is no, I have no idea. I wish I understood better when it works. I also think it's kind of amazing that both of these do prove Erdős-Corrado, like the exact bound. I have no idea why that, it seems like a miracle that that happens. And yeah.
A comment on that. The important part of the Erdős-Corrado bound is the characterization of the sets that meet the bound.
Yeah.
And you can get that from the alpha bound. I don't think you can get it from the ratio bound. Another related comment is that the ratio bound obviously can't be good too often because it can compute it in polynomial time. Okay,
sure.
and getting the alpha is NP hard. And
right, so it's possible to prove uniqueness using ratio bound Erdős-Corrado.
Yeah. So, I mean, in practice, the ratio bound seems to be useful more often, but there are certainly times when the inertia bound beats it, and that's pretty useful.
Yeah, but I do wonder if, I agree that in practice the ratio bound seems much more useful. I sort of wonder if that's an artifact of the fact that we know how to optimize the ratio bound, thanks to both being efficiently computable and all the representation theory that can go into it. And there are some problems where people find some sort of magical weights and apply the inertia bound. So there's a proof of Kleitman's isodiametric inequality using the inertia bound. And I kind of wonder if just it's hard to come up with the good weights when you don't have all this theory. And so that's why it seems that in practice the ratio bound is more useful, but I have no idea. So.
Well, I agree with what you said. Now, one point is that with the ratio bound, if it's tight, you get some information about the structure of coplex. I've never seen any way of getting any information about the structure of the graph when the ratio bound is tight. Okay. The other point is that my comment about relative efficiency is also based in part by looking at certain families of examples. So it's not just so there's in some sense some experimental evidence which makes me think that the ratio bound is not going to be tight as often. But I agree with what you said, and if we need more about it, we want to do better. And the thing that really annoys me is we can't get any information out when we find that the ratio bound is tight.
When the inertia bound is tight.
Sorry, inertia bound is tight.
Yeah. Yeah, I agree. Any other questions?
Is P17 the smallest example?
I believe so. The smallest known example, at least. I think Elzinga, I believe, probably Chris knows the history better again, but I believe it's known that the inertia bound is tight up to graphs of order 10, maybe even 11. But I think, for example, for Paley 13, it's not known whether it's tight. So yeah.
Yes, another question. So the Hoffman bound, it's part of an entire hierarchy. So you can look at order, it's like this sum of squares. Do we have anything like that for the inertia bound?
Not that I know of. Yeah, it's a good question. It's sort of fitting into the general theme that I think is sort of the big thing here is that the inertia bound just seems to have way less structure of every type than the ratio bound. And so I certainly can't rule out that there's some sort of hierarchy that it fits into, but I don't know of one.
I can ask the same thing, like does it have this multiplicative properties like the Hoffman, like the Lovász bound and so on?
No, you certainly, I think you can prove that it doesn't. Yeah. And certainly sort of any proof, any proof you try doesn't seem to work. It's actually just the past couple of weeks, Ehud Friedgut and I tried to reprove Lovász's bound on the Shannon capacity of the pentagon using the inertia bound by examining what happens multiplicatively. And eventually we were able to show that that proof simply cannot work, is what I'm pretty confident of now. So, yeah.
Actually, this example first got me into this really was, if you look at the Cartesian product of a graph with K2, then there are times when that gives you examples where the inertia bound can be useful and the ratio bound is not very good.
Really?
Yeah, so there was a question I was asked about the Canonical graph K94, what was the size of the largest bipartite subgraph? Well, you take the Cartesian product with K2 and then you're just asking for alpha in that Cartesian product. The ratio bound doesn't work, but the inertia bound does give you something very close. Well, for the 7.3, it gives you the exact bound. For 9.4, it misses, and as this order gets larger, this gap gets bigger and bigger.
Cool. I don't know about that.
Well, in any case, I think it's safe to stop sharing. So let's thank you all again. Thank you so much.
Thanks for coming.
Mm-hmm.